Hey everybody! Do I have the music playing in the background? No, I don't. Woo. Luckily, right there, I do not have the music in the background. Oh, there's the music. How's everyone doing? So we got Tiffany here, Carly here, Hannah here, Tara here. And thank you so much to Alyssa right there who does our SI reviews. Alyssa is amazing with the SI reviews. Top tier reviews from Alyssa. So huge shout out to Alyssa right here. If you want, throw out some shout outs to Alyssa right now. Let's see if Mewbot's awake. I went and got coffee. I gave the rabbits some water. So a little break between class right there. Rabbits got some water from New York. Waking up Mewbot right there in the background. Scared? No, don't be scared. Can we do another labeling? Can we do some more probability? Yep, you bet. Can we go over number 9 on the practice exam? I'm confused what formula to use. Yeah, let's start. Tiffany's got first question here, number 9. Who's all here? Can people hear and see me? I'm worried when no one says hello. I'm always worried. Like, am I streaming? Really funny story, really quick. One morning, we can do some true false too. Haley, good to see you here. Hi, Haley, good to see you here. What's up, Wilson? One morning, I started streaming class. I was going for like 5-10 minutes. You're fine, Sarah. I was streaming for like 5 minutes. And I was talking, and then people were in the chat like, "When's class starting?" I was like, "Well, class has started right now." And then people were like, "They're like, is Brian streaming? Is it the video live?" And I was like, "Oh, oops!" And I forgot to go live. So it appears we are live right now. So we'll take a look at number 9 right here on the practice exam. So number 9 right here, I'm gonna do it with the no answer version. We're gonna do number 9 right here. Kayla, good to see you. Another 100 points, everyone. Great to have you here. Let's go check out number 9, sample and distribution of sample mean. Here we go. So this is a sampling distribution means. What is our first step right here whenever we encounter any of these problems? What is our first step? We encounter a problem like this. What do we do first? Whenever we encounter a problem, we're going to start here by labeling our notation. No matter what the problem is, Rock, it doesn't matter. We're going to take this right here. That's a different problem. And we're just going to, well, it's the same problem. Whoops. Another Word document. Psh, we don't care. So this right here is where we're going to start by labeling our problem. And so this one says, many repeated samples of Science 50 are taken from a large population of quantitative observations. Oh, I see something right here. Of quantitative observations that are slightly right skewed and have a mean of this and have a standard deviation of this. So help me out right here. This is your practice. Who knows what notation is not labeled on the screen right now? Who knows what notation is not labeled on the screen? I did music playing good. Sigma is the true standard deviation for a population. Sigma is the true standard deviation for a population, not for a sample. If it was for a sample, it'd be S. But this is the true standard deviation for a population. So, Tara, you are correct. This here is sigma. That is sigma because that's the true standard deviation for a population. And let me ask you this once again. When it comes to the central limit theorem, if this population is slightly skewed to the right with a standard deviation of 2.85, it's not normally distributed. And also, what's the other bit of notation? I need someone to tell me what this is. What is that? What are those? No P and Q. No P and Q. Great job right there, Tiffany. And Wilson right there. Wilson knows that is mu. So right here, mu is 127. It really brightened my day. Someone saw the Mewtwo today and we're like, of course, Brian's a Pokemon fan. He's got Mewtwo as the symbol. Yeah. I made that up so long. I showed my fiance, she's like, neat. And I was like, that's Mewtwo. Yeah, I'm a nerd. And so if we do repeated samples of size 50, will the original distribution of individual observations get more normal? Yes or no? If we do samples of size 50 of this, will the original distribution, the parent population of singular observations get more normal? Will the original distribution get more normal? If we do samples of size 50, will the original distribution... Careful. I'm asking a trick question here. Sorry, I tricked people. 50 points. I tricked people. Will the original distribution get more normal? Is that what the central limit theorem says? The fundamental theorem in statistics. Does it say the original distribution? I.e. this. That's the original distribution. The original won't get more normal. The distribution of the what will get more normal. The original distribution won't get more normal. The distribution of the sample mean of sample size 50 will, I know, right? the distribution of the sample mean of sample size 50 will get more normal. So this is the distribution of the distribution of the sample mean of sample size 50. Kind of like the question number 8 we did. The distribution of the sample mean of sample size 50 will get more normal. And it states that this will have not only the normal shape, and these are on the formula sheet, it'll have the mean of this, and it'll have a standard deviation. Well, let's write it. The mean will still be equal to the mean, and the standard deviation will be the original standard deviation over the square root of n. By doing the square root of n, the central limit theorem states another thing. I will do it right here, Tiffany. We'll explain that. So to Tiffany's question, since this is slightly skewed, what do we need for a sample size? So the conditions right here, now that we have all of our notation written, we'll solve the distribution here in a moment. We'll solve for what this is. After you write the notation, so step 1, mark your notation for any sort of problem like this. Step 2, check your conditions. Condition 1 is always random. Condition 2 is 10%. We'll worry about those later. Condition 3 is where we pause. Condition 3 is where errors occur. Pause to see if it is categorical or quantitative. Categorical, success, failure. Is this categorical? The answer is no. Quantitative is, which Brian can't spell today, is going to be the large enough n condition. And people are stating it properly in the chat. So how does the large enough n condition work? Step 1, we like to put steps on here to make sure we follow it. Find out the shape of the original distribution. What was the shape of the original distribution? So we have to first find out the shape of the original distribution. This problem states it very clearly, and people are correct on what their answers are. The answers for, I think people are on the right track with this. And so put that adjective before it. There we go. Wilson put the adjective slightly skewed to the right. So we will try to make it clear on which of these it should follow. I go by the rules of following: normal, skewed, or very skewed. Like you could say extremely skewed, heavily skewed, insanely skewed. That's when we're getting into like a very strong skew. So will the test say that it's quantitative? It could, or it could say something like we measured people's heights. If it says we measured people's heights, that's the same thing as saying quantitative. Does that make sense, Hannah, right there? If it said we measured people's heights, we measured people's GPA, we measured people's how fast they run a mile, that would all be quantitative. So sometimes you have to look to the question itself. So correct. Proportions are categorical. And so great job, Tiffany, right there. That is 100% correct. Categorical is all proportions, and quantitative is all means. Correct. And there is the mean for the distribution of the sample proportion. It's usually where people get confused. But go to the question itself. We're asking some sort of question where we get a quantitative response. So that's the big thing to look at. Like in the hot water heater, we're asking, does it last 10 years? And that's a yes/no question. So you always want to be like, are we asking a question? Like ask the question to someone. How many donuts do you make a day? I don't know what this is. Like it doesn't say exactly what it is, but it would have to be some sort of like numeric response question. So there's quantitative responses right here to this question. So now that we know the shape, we have to know the size required for the shape. Now, if it's normal, n does not need to be large. This is the large enough n. The more skewed it is, the larger n needs to be. And these go to the numbers Tiffany just said: 1, 25, and 100. Step 3, the last step right here, is to simply ask, is our sample size large enough to meet this shape? That's a good way of stating it right there. Is it a large enough sample size to meet this shape? And so if it's normal, you only need 1 because it's normal already. So rock. It doesn't matter. It's fine. The new distribution will also be normal. If it's skewed, it needs to be 25. So if we're slightly skewed, what number pops into your mind right here? Since it's slightly skewed, what number pops into your mind? Since we're slightly skewed, 25. So we don't need that large of an n. Do we have at least a sample size of 25? So that we say, well, so it's slightly skewed. We say, okay, it's slightly skewed. That's the shape. That's where we say, what was the shape of it? Slightly skewed. So what was our size? Our size is 50. Does that meet the requirement for slightly skewed? Yep. And that's how we check it. The more skewed it is, the larger n needs to be. The more skewed it is, the larger n needs to be. Hence, large enough n condition. If it's normal, doesn't matter. So with the rest of this question, guess what we're going to be doing right here? After we check our conditions, we're going to be drawing the distribution. So the distribution, here we'll do it up here. We've got a little tiny sketch of it, but we want to make this a bigger sketch. The distribution is going to have the original mean. So the mean's going to stay the same, but the standard deviation is going to get smaller, which is the central limit theorem, a fundamental, very, very fundamental theorem in statistics. Because if we meet the conditions, we can actually use the what for it. Why is this so fundamental? Why do we care so much about this? Because if we meet the conditions, we can model it using the what. Why is it a fundamental thing that we can actually then do some analysis on this? Why is it fundamental? Because if we meet the conditions and we can then use the central limit theorem, it states that the distribution is going to look what? Which is the second part of it. It's going to be tighter, and then it will achieve a normal shape. And that's why it's fundamental. It's because like, oh, we can then use the normal model. So we can then draw out what it would look like. So let's draw this out right here. All we're going to do is plug in our numbers. Please notice all I'm doing is taking the numbers up top of where the mean was at of 127.5, plugging that in. I'm plugging in the 28.5 right here. That's a 28.5. Oh my gosh. We're going to have to zoom in because there's no way anyone can read that if I can type 100 words per minute, but I cannot write a legible sentence to save my life. I am trying. This is attempting to write very pretty. So, see, even there, it's tough. There we go. What's so funny is my sister has immaculate handwriting. Her handwriting is pristine. So there we go. I don't think she can type pretty quick too, actually. So, darn it. There we go. There's the mean and the standard deviation. We're actually just going to solve this value right here. So I'm going to go to the calculator right now. Make sure to follow along with the steps right here. We're just going to take and solve that value. So here we go, 7.07. Actually, I knew that. I've done that one a lot. It's a little bit more than 7. So 4.03. That's a nice number. 4.03. So 4.03. And usually the way questions go after this is usually we just ask if something is odd after this. Like usually we have some sort of value that we're going to be asking. Is it odd? Is this unusual? Is it more than so many standard deviations away from the mean? So great. Thank you right there, Wilson, practicing along. That's what we want to do. Wilson, great answers in the chat right there. That's what you want to do. I'm going to round that to 4. It just makes my life easier. I would carry the decimals, but this is just my drawing to help me out. For any sort of question we have. So I'm going to round that. So 131.5, 135. What is Brian doing right here? What is Brian doing every time he goes up one of these? 139. Now this would actually have the extra decimal added on. That would start to be enough to overtake. And actually it would round up on that one too. If we were to put this into the datum lane, that's going to actually round up because it'd be the 0.06 on the side, or 5.6. There we go. So what is Brian doing every time? What am I doing right here? I'm trying to show visually what I'm doing. What am I doing right now? What am I doing to write this distribution? What am I doing? Adding and subtracting these standard deviations right here. Adding and subtracting. Great job right there, Tara. Excellent answers. So we're just taking right here, and at this point it would overtake it and be enough that the decimal would change. Trying to carry that in the background, and then 115.4. So if you do this right here, just take and add and subtract this number. We're just going up and down this amount each time, and then a question would generally ask you, is something odd? We're just gonna break everything. That's what we do right here on Stat Tool 1. Keep adding and subtracting exactly right there. And then exactly not the original standard deviation. This is the new distribution of the sample mean of sample size 50. Great answers, everybody. Great practice. Might do true false after this. You get to pick. Remember, it's your review, your time. It's our time down here. So let's take a look at the question itself and see what it's asking, because we should be able to answer most of these. What would be the average? What would be the average of the sampling distribution of the sample mean? What would be the average of the sampling distribution sample mean? I am so lucky I have this now, because this is what I can do. It's asking what is, oh my God, what is going on? Where do you change the... Oh my gosh. It's asking, what is mu y bar? It's asking, I think I changed the opacity too, but that's fine. It's asking mu y bar. No p times q over n square root for this. There's no p times q over n square root for this, because this is sampling distribution sample mean. So this is equal to mu, and remember we said mu is this, so that is going to be 127.5. Mu y bar is equal to mu, Well, mu y bar is equal to mu, and this right here is mu. So mu y bar is equal to mu. I love that I have this new thing to draw on the screen. It's so nice. Downloaded Epic Pen, got the free version. I might actually buy some Epic Pen. They got a good product. I'll tell them that much. What would be the standard deviation of the distribution of the sample mean? Sample mean, quantitative. This is SD y bar, the standard deviation of the distribution of the sample mean, the standard deviation of it. There's standard deviation of the sample mean, and this is equal to sigma over square root of n. And I need to double check the chat here in a second. It's 4.03. That is correct. And that means we take the sample size right here, n, take the original, and this is stuff we've already solved because we kind of worked the problem to make sure we could solve it. Even if we get any sort of question, we know where these questions are going to go. So that'd be square root of 50 right here. And once again, this is the new distribution is tighter, not the original. The new distribution is tighter and more normal from the fundamental theorem of statistics, which is the central limit theorem, which allows us to use things like the normal. And that's going to be 4.03. So that's those right there. We solved those out on the other sheet. If you want to see a more in-depth solve, check those out. Good stuff right there. Next question going down right here. Love some Epic Pen. All the necessary conditions being met, the central limit theorem, fundamental statistic theorem, which they are, given central limit theorem applies, what would be the shape of it? What's the shape of it going to be if we pass everything? Great question right here. What's the shape going to be? Pen, highlight. Oh, that's highlighter. Oh. Normal. And normal is unimodal. So is 100 tighter than 1? Exactly, yeah. As n increases, it gets tighter. It's going to be normal. How does it do that? Normal. It'll be normal. If you meet the conditions, condition 1, condition 2, condition 3, it is met. Now, for this next one, it asks us about, is something a rare event or not a rare event? So it says, from a particular sample of size 50, 150.7 was observed. Do I still have that up in the background? Oh, I do. So 150.7 was observed. You can answer this question pretty quickly, and actually we would probably count this on the test. With everything we've drawn out right here, is 150.7 unusual or not unusual? Is 150.7, so it's saying a sample mean, and we would take our mean, and we subtract, and we do this right here. So I'll solve this right here. Is 150.7 unusual? And this is 4.03 right here. We solved that earlier. That is solved. And so it is very unusual, and Wilson's right, it's more than 3 standard deviations. Solving this equation right here, 150, that really looks like a 6. I know my 0 sometimes looks like 6s, but that really looks like a 6 today. So 150.7, so we'll just put the solve next to it right here. 150.7 minus 127.5, that's the distance it is away, divided by 4.03 is going to be about 5.7. 4.7. Gosh, I can't do math today. Oh, is it? I feel... Let me double check my math, Wilson. Yeah, you should be right. I think I was thinking 5. Yeah. That's why you double check your math, because I made an error. So we find the z-score. Yep, that's the z-score. Great job right there, Hannah. Excellent work. Some points in the chat. And it's super unusual. So since the z-score here is 5.76 rounded, it's super unusual. So if you use the original standard deviation for the parent population, it's not unusual, but we're talking about for a sample of size 50, this would be unusual. So that's super crazy unusual. That'd be a very, very rare event, and great stuff right there. Should we do the decision tree stuff? I love some decision trees. Let's do a little decision trees right here and see if you could solve the questions. Ooh, sideways output. I remember making this test and being like, this output's so large, we can't get it on the screen. Turn it sideways. Sideways output. Where's the 3.2 coming from? Let me see. Please tell me I didn't close that document. Ah, yes. The 23.2. Where's the 20? Oh, are you talking about the distance? That's the distance these are away. That's the distance between the top right here. Does that make sense, CC? Hey, Josh, good to see you here. The distance these two numbers are away. So the 23.2 is how far 150.7, the sample mean, is away from the mean of the distribution. So this right here is a distance of 23.2, but then we divide it by 4.03 to find out how many standard deviations. Yeah, no, good questions, CC, right there. Great questions. We standardize the difference in statistics because is 23.2 a big difference? Well, we have to standardize that difference right here. We have to standardize that difference. Next question. Put a break in the video. So next question. See if there's Stat201. Someone tagged me in a question here on Stat201. Oh, someone said thanks. Good. I like when I'm tagged with a thanks. Okay, let's look at the next question right here. Let's look at some decision trees. Okay. This apple looks beautiful. Okay. I remember making this question here. So what are we trying to predict for people right here? What are we trying to predict? What are we trying to predict? You should be able to look at this output right here and tell me what we are trying to predict. What are we trying to predict? And then we'll do true false after this, Madison. You got it. What are we trying to predict right here? We're trying to predict somebody's what? We're trying to predict someone's political belief. Are they a mix of political beliefs? Are they more conservative? Are they more liberal? And so whenever you get output like this, you want to make sure you know where these leaves are coming from. If I had a written test, which we don't, I would do the one. I wanted black. This is leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. Which of these is the smallest leaf? Which of these is the smallest leaf? Which of these is the smallest leaf? You can see it visually and you can see it numerically on here. Which of these is the smallest, has the least people in it leaf? Not leaf 2. Leaf 2 is the second smallest. Leaf 4, no worries, 100 points in the chat, don't worry. Leaf 4 is the smallest, there's 16 people. There are 16 dots if you count them, 1, 2, 3, 4, 5, 6. It might be a little hard to count, they're a little clustered in there. But this would be leaf 4 is the smallest leaf with 16 people. And you can see the breakdown. There might be 2, 3, and maybe 11, something like that. It's hard to tell, but you could actually see the amount of people in the leaf right here. Now, how do we actually want to see how many people are in the leaf? We're not going to do it by counting. You could. It's just some leaves have a lot of people. We're going to go down here to the leaf report. Now, it does have the questions. I'm only going to take the numbers that we can see right here. I'm going to turn it so we can see it much better. This was a written test, so people could actually just turn their sheet sideways. So we're going to take this output right here, and we're going to turn it sideways on our output. Do I still have just that one? Yes, nice. Yeah, there it is. That leaf, tiny leaf right there is hard to see. A little tiny leaf. So let's go right here, and let's make it so we can see this output at the same time. This is the leaf reports. We're going to put it on the same page. Oh, really? Shrink down. There we go. Okay. I tell students never do that. I say, don't do that. You change the aspect ratio. Okay. Let's relabel stuff right here. Don't change the aspect ratio on image. It's going to make something stretched. You don't do that. Bad idea. Don't do that, Brian. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Of the people who go to church at least once a month, what % of them are more conservative? Of the people who go to church at least once a month, take a moment right here, see if you can solve it. Of the people, let me write the question. Of the people who go to church at least once a month, what % are more conservative? There we go. Everything's on the screen. See if you can solve this out right here. Who's got it? Take a moment, see if you can solve it. Would you know how to do this? Of the people who go to church at least once a month, what % of them are more conservative? I'm taking a moment to solve it myself. Got it. Well, I haven't... Well, I've got a guesstimate of what it is, but I know the mathematics of what you should do. Like, I have the equation in my head. I just haven't solved it. Should be about 60% or something. Who's got it? Can we briefly go over all the different variables? Yeah, we could do a formula sheet review. I think someone has a question about true false after this. It might be 59%, Hannah. Hannah, how'd you find that? Explain theoretically. We need to know the theory behind what we're doing. What percent of people who go to church, of the people who go to church at least once a month, what percent are more conservative? What color on here is more conservative? Red, green, or blue? What color on here is more conservative? What color on here is more conservative? Yep, Hannah, that's the correct equation. Great job, Hannah, right there. Hannah solved the mathematics correctly. Great job, Hannah. And we're going to see how Hannah solved that. What color on here is more conservative? Just take a look at the graphic. Take a look at the way these are ordered. And you could go up here to the original if you had this and be like, okay, I got it. What color over here is more conservative? What color is more conservative? It'd be up here at the top. You see how more conservative is the second one. So right here, this is a mix, blue, more liberal, red, and more conservative, green. And then also in the order by which it goes, more liberal, more conservative, a mix. So the more conservative is the middle one, and it'd be the green one. So where do we want to look? I'm going to shade some stuff for you to look at. Do you want to look here? Do you want to look here? Or do you want to look here? Which thing are you going to look at when I say of the people who go to church at least once a month, what percent of them are more conservative? Which color are you looking at right now? Where are you looking on this screen? Where are you looking on this screen? Oh, I've corrected that, Vincent, right there. I've corrected that. Yep. So make sure to do the corrected version. I corrected that last night. Sorry about that, Vincent. Sorry. I'm very sorry about that, Vincent. Vincent, 100 points pointing that out. I got an email. 2 people emailed me, and then I went and corrected it last night. So you might have the old version. It's 0.03125. That is correct. I don't know why the keys changed this semester. I was like, what the heck? I think people thought we could make them look nicer by typing the answers, but... So the blue portion right here is only people who go to church once a month. And so with this right here, that means the blue must be the combined totals of what? Explain to me in words. The blue must be the combined totals of what? Of leaves what and what? The blue must be the combined totals of leaves what and what? You're welcome. Thank you, Vincent. Yeah, of course. Anytime. Nothing for mentioning that. That was an error. Combined totals of leaves 3 and 4, which means we would take right here and combine this up here and this up here. So that green right there is the total of the people in leaves 3 and 4 who are more conservative. How many people are there in leaves 3 and leaves 4 when you add them together? How many people would there be? So you're adding together what numbers right here to get the total for that. Because the 317 people are divided up into 301 here and 16 here. What are you seeing for these people, and how many total would there be up here? Like, how many total is that green? That green is how many, because you're taking these people. These are the 301 out of the 317. These are 16 out of the 317. See, those add up to 317. And you would have here these numbers here. I'll make it easier so you can see how many total would there be now. How many total would there be? 186. That's 186 out of the how many people in this leaf? That's 186 out of the, people might be saying that, 317. Exactly. Great job right there, Carly. Make sure to kind of, like when you're doing this, draw it out. Make sure it makes sense to be like, oh, well, I'm looking at the people in this leaf. They're divided, because you're dividing them into like smaller groups right here. 186, because exactly, CC, great answer right there. Yep. That's exactly why it's 186. Thank you, CC. Great clarification right there. 186 because you're adding them back together. You're kind of merging them back up into that upper leaf. What does this represent right here? What does that number represent? What does that number represent? That number in pink highlighter. That number is actually what? What is the leaf display above that one showing? Is that, Griffin, is you talking about this one? That's the total amount of individuals, the total amount of people surveyed, and then they're subdivided down further, like they're split apart into groups. Griffin, is that what you're asking? Clarify the question. Great job, Griffin, 100 points. Go into detail, keep asking. That's the total amount of individuals who are surveyed, and then you see we're splitting them apart. That's what the partition models do, known as decision trees. It partitions the data into groups, and then you see down here the final groups where this 628 people have been split apart. Now, you could merge these back together into this because these people, these 317 are split apart into a smaller group right here. So these 317, why are you doing that to me? These 317 are split into these groups. These 311 right here, great band, are split into these groups. So, but each time we split it down further, partitioning the data into groups based on X variables to understand some sort of variation in a Y. I think that's got it. The next thing we're doing, let's take a vote right here. I think I'll let you vote. We can do true/false. We can do review sheet. Let's do notation on review sheet. And if 320 hops in, 320 has a test tonight. 320, you can ask some questions. 2 tests on the same day. Woo! I love that too. Or we could do probability problems. And so let's ask the community on that. After true false, yep, take a vote. The vote is on the screen. Take a vote on the screen, which things you want to do. And we'll do that. Your vote, your choice, whatever wins, we'll do. And we'll probably spend like 15, 20 minutes doing it. And then we'll hop to the new topic. 320, if you swing by, ask questions, any questions you have. We'll give this another 30 seconds. So if other things I think you should know, true false is crushing it right now. Looks like we're doing true false. Some of the things I think you should know right now are how to do interpretations. Ooh, starting to tie up now. Interpretations. What are the 3 things you should know interpretations on instantaneously? Let me get that up and going. What are the 3 things you should know interpretations on instantaneously? If you're watching this review right now, can you post the after? Yep, I'll post. I'll send that out to before class starts. That's at 2:50. What are the 3 interpretations you should know? I'll send that to the whole class. I don't post it here in chat because since this is a public video, I don't post it in chat. There's part of it. Here we go. You should know these instantaneously. If you're watching this video and you weren't in the morning review, make sure to know these. Make sure to have the slope interpretation, the intercept interpretation, the R-squared. We could go over some of this later, but make sure to have these. Maybe 5 to 10? I didn't count. We used to put them at the very end and do like about 5 or 6. Thank you everyone who voted right there. So true false is winning, probabilities next, and then review sheet is last. We'll revote here later. Let's go do some true false. Here, I'm gonna put a break in the video so we can mark it. True false coming up right here on Stat 201. Let's do some true false. So I'm going to come up with some questions right here. Think through them as we do this. What top of the part? The top part of the leaf report. Oh, that's probabilities. Thank you so much, Kayla. 100 points. That gives you probabilities. I don't like the way they're estimated. I think it's like predicted probabilities for future. We don't actually use that one and we don't always supply it. So the top part of the leaf report, I see what you're saying now. The top part of the leaf report is usually probabilities for individual leaves. Great question right there, Griffin. And thank you, Kayla. And so Griffin re-asked it. That gives probabilities. Usually we go with the counts in the leaves. Thank you, Griffin, for asking that. Do you know how many types of each question will be on the exam? It's a mix between, well, there's 3 written responses, 3 interpretations, slope, intercept, R-squared. There'll be multiple choice, true, false, and numeric entry. Multiple choice, true, false, numeric entry. And that's the majority of it. And then there's 3 written responses. Good stuff right there. Hopping in, doing some true, false. Let's do it. True, false questions. True, false. Okay. Let's see right here. So all of these will be answered true, false. The central limit theorem states that the distribution of the sample mean will become more normal and tighter the larger n gets. The central try to do 10 of these. So be thinking these over, be talking in the chat. 2 seconds. One more song, we'll have it. Oh, be conversing. Let's see how good people do at this. If this was the test here, how would you do? I'm gonna try to come up with 10 right here. Like I'm jumping chapters right here. Like I'm thinking of other chapters. I'm like, what other chapters? Last question. No, it's watching that right now. Okay. There we go. We got all the questions on the screen. Let's start at the very beginning. Very good place to start. Let's see what people have. Question number 1. The central limit theorem states that the distribution of the sample mean will become more normal and tighter the larger n gets. True or false? The first question on the screen right here, true or false? Let's hope we get the same colors today. You're going to go red? Good, that's red. We're just going to check our colors. We'll mark what's wrong about these if we have a wrong portion, but is that true or false? 1 is very, very true. 1 is extremely true. And it's important to note, like we'll talk about these just briefly right here. It's important to note that we're talking about the distribution of the sample mean. What does not change? What does not change? So I'll make these a little bit smaller so I can actually do a little bit of drawing below these. We're talking about the first one right here. What does not change? I'll zoom in. There we go, and then we'll see it better. What does not change? The original distribution. The original distribution, like if you have an original distribution, we'll erase this here in a second, but if you have your original distribution is like skewed, so the original distribution looking like this, well, that's not going to change. The distribution of the sample mean will change. The distribution of the sample mean as n gets larger gets more normal and tighter by a factor of the square root of n. So the original distribution, which is where you draw these from, and you take a sample of sample size 50, and then one blue dot down here, I'm using blue because that's what the applet uses. One blue dot is the what of all these samples of size n. So as n gets larger, they're going to take the what of n to get the distribution of the sample what, because that's the distribution of sample somethings of sample size like 50. That's the distribution of sample whats. Of sample of sample whats. I think Kayla's right there. That's the distribution of sample means. So it states that the distribution of the sample mean, not the original distribution, will get more normal and tighter by a factor of the square root of n. And if we have a large enough n, it will be normal enough. The central limit theorem is super important. Some might say it's fundamental to statistics. True or false? The central limit theorem is super important. And why is it super important? That is super true. And why is it super important? Why is it super important? Because if we meet the central limit theorem and we have a distribution that looks like this, and then we meet the central limit theorem, we can start to do what to describe the shape of the sample mean. We can start to use a what curve and then actually calculate probabilities. So why do we use it? Like, why is it fundamental? Why is it important? Because meeting the conditions means we can model it with a normal distribution. And then we can talk about probabilities to say what percent of the time would it be above a certain mark, and we can figure out probabilities and say what we expect. Imagine I asked you this. Shipping times are normally distributed with a certain mean and standard deviation. If you have 100 shipments, what would you expect the average shipment time to be? You could use the empirical rule. You could use the empirical rules then to say, we would expect a mean right here above this to only occur 4% of the time. If you're in supply chain, would it be important to report to your customers that only 4% of the time would your 100 shipments have a shipment of this average time right here? You'd say, well, the average shipments for 100 shipments shouldn't go above this. We'd only expect this about 4% of the time, so that's pretty unusual. Imagine a client's complaining. And you say, well, that's a pretty unusual observation that you had right there. We're very sorry for that, and we're going to do a refund. But imagine if a client started complaining over here, where it was a little bit above. If a client started complaining over here, you might say to them, we're very sorry. It depends on probably how big of a client they are. But would you be super concerned if a client started complaining over here where their shipment time or a higher shipment time might occur like 40% of the time? So now their shipments are a little bit late, but they've had 100 shipments. And you're like, well, there is variation in individual shipment times. Like individual shipment times have a lot of variation, but on average for your 100 shipments, the shipment time should be more normally distributed. Their average for 100 is a little bit above average, but it looks like it's a very what observation for their shipment times. It looks like their shipment time is not that unusual, right? Even though it's a little bit above average, you'd say, well, we're very sorry. You might try to be nice to them, but you're not going to go to the people who work, for you and say, hey, there's a problem here. You're going to go and be like, yeah, they're complaining because it's a little bit above average, but it's just normal variation from what we would expect. Like we know our shipment times. We know the variation in our shipment times. And so the shipment times they're seeing are a little bit above average. It's a little bit above the mean, but it's within kind of what we would expect. And you could do the Z-score for it. And this is why it's fundamental, because we can understand the variation. So if you do things like supply chain, super duper important right here. That's why we love statistics. It lets us understand what's going on right here. It's still on the curve. Exactly. It's like if you're in customer service, you're like, oh, I'm so sorry. You're like, this is not that unusual. Because we can mathematically tell you we would expect this. This is about what we expect. It's a little bit above average, but it's close enough to what we would expect that it's not unusual. Z-score. Cluster sample acknowledges the differences and samples according to those differences. What's false about... what's false about this? Cluster sampling acknowledges a difference and samples in accordance to that difference. What's false about that? Cluster sampling acknowledges a difference. Help me out right here. Who's got it? I can tell you all the answers, but remember, better if you practice. That's stratified right there. Kayla, 100 points for the chat right there. Kayla, you got it. That's stratified. So this is not cluster sampling. If you're talking about acknowledging a difference, it's going to be stratified. Great job right there, Madison, and also Hannah right there. Two events that are independent can be easily multiplied together. Rotary strata. Help me out with the next one. We're trying to mark what's false about these and make sure we make clear. Clustering has the census, correct. Whenever we do a cluster, we'll focus on things are randomly assigned to groups. We randomly take those groups and then we perform a census. 3 steps. Put those steps down if you don't have them. So what is number 4, true or false? Exactly. We can multiply independent events. I do want to point this out too. So 2 events that are independent can be easily added. So if we're adding things, then we'd probably want to say disjoint. Do note, color changing pen, you are driving me nuts today. Microsoft Word, help me out. Do note on the formula sheet, it literally tells you these things. A or B is the probability of A plus B, and the 2 events need to be mutually exclusive, which is disjoint. So A and B is multiplying, and they need to be independent. This is the multiplication rule. Should be pretty clear. And these are on the formula sheet right here. We don't talk much about the empty set. I don't think we've ever put a test question about the empty set. It's just things that can't occur. And this is the set of all events is equal to 1 if you add up everything. So the formula sheet's got a lot of good stuff right there, but it does literally have the addition rule. When we add together 2 events, probability of A or B, they must be mutually exclusive. And great job right there. Disjoint could be added. Exactly. 2 events that are complements are dependent. Ooh, who thinks they know the answer to this one? Who thinks they know 2 events that are complements are dependent? Here's my question to you. You can only win or lose a game of college football. Does winning depend on losing? Does winning depend on losing? That's the same answer to this question. True. So if you have things like win or lose, and win has a probability of 70%, and lose, which we're saying you can't tie, this is only you can only win or lose this game. If you win or lose, if you win the game, you don't lose the game. Winning is dependent on losing. Now, disjoint and independent are not the same thing, because now, or disjoint and, yeah, they're different terminologies because we have to watch out. If we were to add in tie right here, these are no longer complements. Each one of these, if you want me to review exactly what each one means, we can go into it. These are no longer complements. You now have the set of things, either you win or you do not win the game. So now we have you either win or you do not win the game. So it could be described complements here. You either win or you don't win the game. So those are still complements, and they are very dependent. Not winning is dependent on winning. If you know someone lost the game, they did not win the game. So all of these things right here are very dependent. What does dependent mean? Knowing somebody lost the game would mean what? I would know what? If something is dependent, knowing things are dependent, what is the definition of dependent? What is the definition of dependent? What is the definition of dependent? To say something depends on something else. I'll give you the answer here in a second, but think over it for a second right here. Dependent means what? Knowing one thing tells you something about another. Exactly. Not quite complementary, though, because these are all dependent now. So good answers right there. So not quite complementary. It means knowing one thing tells you something about another. Does having school depend on snow? Does having school depend on snow? So the definition of dependent would mean knowing one thing tells you information about another. If one thing depends on something, knowing this tells you things about this. Does school depend on snow? Does it? Well, no, but would knowing it snow tells you anything about school happening? So does school depend on snow? It does, right? Knowing that it snows tells you something, but no, so they're not complements. So they're not disjoint. They're not complements. This is where we start to combine terms together. All dependent means is that knowing one thing gives you information about another. Does that make sense? So if I know it snowed, would that tell me anything about the possibility of school? Knowing that it snowed would make school what to happen? Knowing that it snowed, i.e. it's going to be dependent, knowing that it snows would give me information that school is going to be what? Like, you're like, man, I've got a lot of assignments due tomorrow when I have to go to class. Back in the day when you have to actually walk into class and turn your assignments, knowing that it snows is going to make school less likely. School could still happen, so they're not disjoint events. So be very careful. People start to combine these things together, but just go to the basic of what dependent means. But once again, we use the classic examples right here where Brian gets coffee and Darren gets coffee. Knowing that Brian got coffee, which has a 98% possibility, would tell you what about Darren getting coffee? Darren has a 30% probability of getting coffee. This is Brian and his brother Darren getting coffee. Knowing Brian got coffee would tell you what about Darren getting coffee? Darren's in a different state. We don't talk every day. I'm not like, hey, Darren, I got some coffee. We don't do that. It would tell you nothing, which means these two things are what of each other. Since it tells you nothing at all, what is this going to be? Brian getting coffee is completely what of Darren getting coffee? So if you know Brian got coffee this morning, like, well, what does that tell me about Darren getting coffee? It gives you no information. Knowing Brian got coffee, which people are saying independent, and that's what independent means. Knowing Brian got coffee would tell you nothing about Darren getting coffee. Are these events disjoint or not disjoint? So are these events down here disjoint? And looking at the probabilities, because if they're disjoint, we can add them, which is pretty easy to answer. And here's the definition of disjoint, Catherine. Thank you so much. 100 points, Catherine, for asking that. They are not disjoint. And the way to check disjoint is the following. We ask, let me zoom out just a little bit here. There we go. That works right there. To check to see if things are disjoint, we ask, can Brian get coffee and Darren get coffee? Can they happen at the same time? If something is disjoint, they cannot happen at the same time. Events that are disjoint would look like this. Brian gets coffee, Darren gets coffee. But in truth, what could happen with these events right here? In truth, it's not that Brian gets coffee and Darren gets coffee and there's no overlap. What could happen with these events right here? It could be that Brian gets coffee, what? So what could happen with these events right here? Because they're not disjoint. They're not disjoint. Brian could get coffee and Darren could get coffee. If things are disjoint, when one happens, the other can't. They have no overlap. And if they are disjoint, you could what to these probabilities to figure out the probability of Brian getting coffee and Darren getting coffee. If we have Brian getting coffee or Darren getting coffee and they are disjoint, we would be able to what these two probabilities. If we have not multiply, so if they're disjoint, we could add them, right? And they might not always add to 1. If they are disjoint, so once again, here, I'm going to show this again. Use your formula sheet to your advantage. If things are mutually exclusive, which is disjoint, you can add them together. Use the formula sheet to your advantage. It literally is like a cheat sheet in this way. You can't have a cheat sheet, you can't have nodes. But if they are mutually exclusive, which means disjoint, you can add them. So an AND is AND means we're doing the independent right here. Do you see the AND right here? That's going to be the multiply right here for independent. So if we multiply two things, we need to check to see if they're independent. If we are adding two things, we need to check to see if they're disjoint, i.e. mutually exclusive. I'm pausing right here so people can see this. This is a huge like cheat sheet helper if you know how to read this, that when I say, what is the probability that Brian gets coffee or Darren gets coffee, I'm asking if we can add these right here. You get to print this out or write it down. Just make sure to show it. Great question right there, Colin. Thank you for asking. 100 points. So AND is multiply or is disjoint, which was adding. Great job right there. Kayla notes right there. Good practice. These are the ones people usually get confused, hence why we're pausing on these and reviewing concepts. But what if I change these to grades? So now I'm going to ask you about grades. You ready? Now we have the probability you get a B in this class or you get an A. And you guys are great students. You're here right now. You're going to put a 70% probability of a B. So you have a 70% probability of a B and only a 2% probability of a D. So are these events disjoint? Yes or no? Are these events disjoint? In the chat right now, yes or no? Kayla, rockstar Kayla right there, 100 points. Thank you so much, Kayla. Are these events disjoint, yes or no? Yes. Because if you make a D, what? Explain to me. If you make a D, which is a smaller probability, we'll shrink it down a little bit here. If you make a D, what? You know someone made a D in the class. What does that mean about making a B? They're not complements, though. If you make a D, you can't make a B. So knowing someone made a D means a B is impossible now. That's what disjoint means. Are these events dependent? Would making a B depend on making a D? Be very careful. So yes or to the next one. Would making a B depend on you making a D? Are these dependent? Are these dependent? Would making a B depend on making a D? Are they dependent? Would making a B depend on making a D? So would you making a B on the class depend if you made a D? Like, you know someone made a D. Does that tell you any information about them making a B? I want in caps the answer to this. Type it in caps. Like, some people put yes or no, but I'm going to keep asking it. Knowing somebody, I'll be careful. Knowing somebody made a D, would that tell you anything about them making a B in the class? If you know, your friend's like, man, I made a D in the class. Would you be like, so did you make a B? Do you hear it? Knowing somebody made a D would tell you everything about them making a B. In this instance, making a B depends on making a D, which means we cannot do what to these events? We cannot do what to these events? We cannot say the probability of making a B and a D events. That is correct, Hannah, right there. That's correct theory, correct. So what can we not do? And so Hannah, excellent job right there, 100 points. We cannot what these events. I can't say the probability. We can add them because they are disjoint, because you can't make a B and make a D, so they can be added, but we cannot what them because they are dependent. So since they are dependent, we cannot multiply. Once again, this is a good review right here. These are the tougher concepts. We cannot multiply them because they are not independent. They are dependent. So all disjoints are dependent, but not all dependents are disjoint. That is correct. Let me double check my brain. Anything that is disjoint like these has to be dependent, but not all dependent are disjoints. Exactly. Because going back to the previous example, last example right here, well, these are not dependent now. Oh yeah, so let's do school and snow. Last example on this, really great review. These are tougher things. These are the big concepts. So we have here school, and so put school has a 99% probability on any given day, and snow has a probability of only 1% in Knoxville. So now we have two events. Does school depend on snow, yes or no? Once again, the review right now. Does school depend on snow? Does school depend on snow? So in Knoxville, there's a 1% chance of snow any day, and school has a 99% chance of being in session. Does school depend on snow? Yes. If you know it snows, school is going to be less likely. Are these events disjoint? And what do we mean by disjoint? We'd be asking, can we have it snow and can there be school? That's when we're asking, if there's an overlap, it's not disjoint. Are these events disjoint or not disjoint? Like, can it school and there also be snow? Can it school? They are not disjoint. So now we have two events that are dependent but not disjoint. And always walk through and be like, okay, wait. If school is dependent on snow, that means knowing it snows would tell me something about school happening. Well, if I know it snows, school is less likely. Are these events disjoint? Well, if they're disjoint, if it snows, we can't have school. If there's school, it can't snow. So these are not disjoint because there is this right here. I hope this has helped out with the terms of disjoint, complements, and also when to use the rules. This is a good review right here. We covered a lot of the chapter right here and when to use. Please, once again, I want to say this. We're going to go back to the true false right here. Please use the formula sheet to your advantage, seeing when to use this. What is another word for mutually exclusive? What is another word for mutually exclusive? Mutually exclusive, like they exclude each other. Disjoint means they can't both happen at the same time, which... That's right there. Same word, same word. Great job right there. Everyone, great job, everybody. Okay, let's hop back to our true-false practice right here. Decision trees use multiple y's and one x. Decision trees use multiple y's and one x. Decision trees use multiple y's and one x. What do we got right here? False. False. It's false. It needs a switcheroo. Multiple x's and one y, so these need to be reversed right here. That's the reversal. R squared tells us the strength and direction of a regression. R squared tells us the strength and direction of a regression. I love the jokes. We need more jokes. If you ever have a joke or saying, oh, Kayla, you know what we got to put some quote 113 in the class. Quote 113 will never be forgotten. Do monotone lines false. Okay, I'll try to focus. Serious face. This is false. What do we like to say here? R squared is not this. Oh, that's... oh, it's quote 112, isn't it? What is... that's a quote from yesterday's class right there. Quote 112. R squared is not correlation. Who knows? I'm going to start you off right here. Who knows the interpretation? Fill in the blank right there. Blank percent of the... I'll pull up the sheet right here so we can see it. Let's go through the millions of sheets. Remember this, I can tell you all the answers, but you need to practice blank percent of the what? Blank percent of the what? When you get to R squared, what's going to go through your mind? Blank percent of the what? What's going to go through your mind here when you get to R squared? Blank percent of the what? We'll go to one of our answer sheets right here. Well, there it is. Blank percent of the what? Well, that is correct. Blank percent of the what? Of the variation in y is explained by the variation in x. Great job right there, Hannah and everybody. Blank percent of the variation in y is explained by the variation in x. We were doing some practice here earlier in class today. 4.9675% of the variation in somebody's GPA is explained by the variation in number of drinks per week. And we did some intercept and slope interpretations. Have these down. Practice these. So R squared is not correlation. Great job right there, Carly. Excellent work. And then what do we always do to the value of R squared? What do you notice happening here to the value of R squared? Very important thing that some people forget. It's not correlation. Don't talk about it like strength, direction, form, unusual features. It's going to be the variation in y. If we go technical, like we do in 320, it's going to be the reduction in the sums of squared error from the naive model. Pretend I never said that. 320, we'll talk about that. 30% of variation, R squared, yep. And so what are you going to do to it? Turn it into a percent. So you got it right there, Hannah. And what will you do to it then? You will multiply it by, but to turn it into a percent, which you are correct. To turn it into a percent, more points in the chat. How do you turn percent? Multiply it by 100. Yep. And great job, everyone here following along. This is your practice. You got this. Get it down. Let's look at the next true false. The 10% condition says we need to sample more than 10%. Pretty easy one right here. 10% condition says we need to sample more than 10%. What do you think? What do you think? Coffee time. That's what I think. Less than 10%. I'll be so excited if people make 100. A lot of questions. Not trying to scare anybody. I think test 3 is going to be easier. So if you get like a 75, 80 on this test, be like, woo, toughest test out of the way. If you get an 80, be proud. I am not joking. If you get an 80 on this test, I want you to be proud because you're probably doing all the homework, you're probably doing all the quizzes. I think test 3 is going to be easier. If you make an 80 on this test, I want you to be proud and be like, yes, tough test out of the way. And then test 3 is the final, right? And then test 3 is more repetitive. No, don't be scared. Test 3 is going to be easier. I think the average tonight is going to be in the low 70s. There might be a curve, but I want you to be proud if you make an 80. I want you to be like, yes. If you make an A, I want you to be like, I want you to throw a party if you make an A. Because truthfully, I can make an error too on this test. I think the hardest part about this test is that there's a lot of material. I think that's the hardest part. None of the material is super hard in and of itself, but you got a lot of little bits. Little bits. But do not freak out. I think test 3 is going to be easier. So if you make an 80 on tonight's test, I want you to be proud. If you want to make a 70, I want you to be okay with that. But you got this, Kayla. You got this. You got this. You got some great answers here. Don't second guess yourself. You got this. I have faith in you. You got this. I believe in you. I think it's the hardest part. A lot of material. Probably the toughest test right here. The success failure condition, which is used for quantitative data, states that we need at least 10 successes and at least 10 failures. Oh, we can probably do that, John. Probably that. And I did some yesterday over those. I did some example problems yesterday, and those videos are marked. And we will have afternoon class. Yep, and I'll send out the video for that. If you make a B, be like, make a B. Because remember, the tests are the harder part of this class. The quizzes, the homeworks, the Canvas content, we get some great grades on those. Careful, careful, careful. Careful, careful, careful. Every time we get to condition 3, we always ask, is it quantitative or categorical? So this would be questions. And the success failure condition isn't really about like binary stuff, even though we use it for binary data. It says we need at least 10 successes, at least 10 failures. So the way we check it is NP and Q greater than 10. So this one here is false. It's got, I threw that little, that's a mean trick. But that one's pretty tricky right there, which is used for quantitative data. It's the false portion of this. So you'd be like, no, that's wrong. It's for categorical data. The condition is stated correctly right here that we need at least 10 successes, which is NP greater than or equal to 10 and NQ greater than or equal to 10. That is false right there. If the data is normally distributed, the large enough N condition would be satisfied for an N of 1 when the original data is normally... I restated it. That last part's not needed. There we go. Large enough N condition will be satisfied for an N of 1. Correct right here. I think the successor is categorical. Like that was your data is either successor. Like, nice job, Kelly, right there. Yes, this is true right here because the numbers are 1, 25, and 100 for normal and for skewed and for very skewed. The more skewed it is, tell me about it. The more skewed it is, the wider N needs to be. The more skewed it is, the more skewed your original distribution, the wider N needs to be, which you need to look at the shape of the distribution. The more skewed it is, exactly, and it's already normal, so it's going to be more normal, so it's already normal. The more skewed it is, the larger N needs to be. Well, let's take a vote right here. If you're 320, you're welcome to jump in. You do have an exam tonight too. Where's my 320 at? What should we do next? We have notation. Chat, just go crazy with some answers right here. I'm going to go to the main screen. Let's go to the main screen right here. Let's do it. So in the chat right now, go ahead and give your votes. Tell me. Let's listen to a song we know. What do people want to cover right now? Skewed. Skewed means it's going to be more like not normal shape. So it's going to take more to normalize it, a larger N. So this skewed wouldn't mean smaller. Skew requires a larger N. Well, like skewed requires 25, heavily skewed requires 100. So the more skewed it is, like more extreme the skew, the larger the N needs to be. We have ways of looking at this more complexly with like actual tests for normality and upper level statistics. But for our purpose, the central limit theorem, we think of just like in a simpler sense that if something is more skewed, N needs to be larger such that the distribution of the sample mean will be more normally distributed. What shall we look at? Your call. It is open floor right now. We had a lot of suggestions. Oh, the sample size. Skewed means it's smaller. Oh, yeah. Oh, great. Yeah. Kayla, you got this down. You got this down. Bring some confidence tonight, Tess. You got it. Probability question. Probability question. So people want some 320. Charlie, ask a question for 320. We'll do that next right here. We'll do probability 320. What do you want covered for 320, Charlie? Throw your question in the chat. Say, hey, can you cover this? And we'll cover some 320. We could probably do that at the end right here because we have regression for 201. So we could talk some 320. People are saying probability. Probability. Okay. Chapter 12, probability questions. Multiple people saying it. Thank you, everybody. And thank you to... We've had so many people helping out with answering questions. I've missed a few, and people have helped out clarifying. I want to do this right now. If you're here watching the exam review right now, I want to say a big thank you and throw out 1,000 points. Big thank you to anyone watching the exam review right now in the chat. Huge points. We sometimes do some craziness here. Today, let's do it. Okay, so crazy points in the chat. Probability with the mean. I'm starting to do it with the normal curve. I can do some of that stuff next right here. And so we're going to try to do some 320 after this. Charlie, put a question for 320 in the chat. Be like, hey, can you clarify this? Can you talk about these concepts? And we'll check that out. So with this, people are checking out the points. Like, oh, just got 1,000 points. People are getting near the limit. People are getting near the limit. How do we figure out if the sample size is large enough? So what steps do we look at to figure out if the sample size is large enough? 1, we look at the shape of the original distribution. And then 2, we see if we meet the sample size for that shape. So we want to look at the shape of the original distribution. And then we look at this, the sample size required for that shape right there. That'll be the steps for seeing if we have a large enough n. And so now, let's take a look at a probability question right here. So with this, Brian is playing basketball against his brother. He will play 2 games against his brother. Brian is horrible at basketball and only has a 20% probability of winning a game. With the 2 games, what is the probability that they each win 1? Tougher question right here. Kayla just rock star right there. Kayla, great job. And I think was it Sums of Square stuff? Yeah, let's take a look at that. Let's probably look at ANOVA here next. Okay, so take a moment. See if you can solve this. Let's see what answers we got in the chat, and then I'll solve out this problem. Brian's playing basketball against his brother. He will play 2 games against his brother. Brian is horrible at basketball. Only has a 20% probability of winning a game. With the 2 games, what's the probability they each win 1? So usually, I'll start marking some notation right here. Once again, whenever we get to a problem, we're going to mark the notation. Okay. It needs to be at least those. At least those. Great question, Griffin, right there. At least those. Depending on the shape. Depending on the shape. So there's the probability of winning. And we're not going to tie. My brother and I are not going to tie. There's going to be a tiebreaker. You got to have a tiebreaker. When you're kids, man, you got a tiebreaker. You don't end that game and say we tied. There's got to be a winner. There's got to be a loser. Sorry for this game. Great job. Thank you so much. Another 100 points. People helping each other in the chat right there. Has anyone got any guesses on this question right now? Starting the solve on it right now so we can figure this out, but see if you can solve it. With 2 games, what's the probability they each win 1? I think I know the answer. Has anyone solved it? What do you get? Let's see. There's a few ways to solve this problem. There's a few ways to solve this. See if anyone gets it. 100 points in the chat if someone can solve this. I'll solve it here in a second. I'll put a 1-minute timer on just to make sure I don't go too long. I don't know, 30-second timer. So after 30 seconds, I will solve this problem, but I want you to take a shot at it and see if you could solve this. See if you can solve the answer to this. You want to imagine you're seeing this. Close, Catherine. Close. Catherine, you're super close. You're very close, Catherine. Catherine, 100 points in the chat. You're close, Catherine. Close. So that's the same. So close. People are close. Abby is correct. Another 100 points in the chat. Abby got it right there. Abby is correct. Abby has the correct answer. Let's take a look. And You want to imagine this. So when you're imagining this happening right here, what could possibly occur? Tell me about the things that could occur when you imagine this. Imagining this, Wilson's got it right there. We have win, 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 loss, loss, win, or loss, loss. These are the events that could occur, and the probability of these events right here, that just stands for probability of the events, are what? Well, the probability of the event of win-win is what? Go ahead and someone tell me in the chat. That is correct right there. Great job, Catherine. And the reason you're multiplying by 2 is you're actually adding them. Interesting, right? So people are solving it right now, seeing how to solve it, and hopefully drawing this out also helps with visualizing it and seeing that the probability of win-win is going to be this right here. The probability of winning both is 64%. That's the probability, that's lose. Win-win, oh wait. Multiplying wrong events, probability of lose-lose. I was like, I'm not that good of a basketball player. I was like, something theoretically just sounded wrong to me. I have a 4% chance of winning both games. Win and win. So what's the probability I win and I win? Then what's the probability I lose and I lose? And you know what's really interesting about this problem right here? The probability right here, if you think about what we've just done, how could we possibly solve out for these right here, which are the probability of winning one game? We both win one game. How could we solve out this area right here? So we actually can solve it a different way, which a lot of people are seeing how to solve it. Josh, great answer there, Josh. You're seeing how to solve it. So this has to add up. Like, we can theoretically tell that these probabilities right here have to be this, because the whole sample space has to add up to 1. If you add up these numbers right here as the whole sample space, it has to add up to 1. So, well, the individual probabilities, so Wilson, if you want the individual probabilities, each of them would be 16%, but then the whole thing is 32, which I think Wilson sees right there. Great job, really great practice. And drawing these things out, like on your scratch sheet of paper, is the key to being like, let me see right here. The probability of winning and then losing a game is this, and that is equal to 16%. And then you could add these together because you can't lose and win and win and lose. These are disjoint things occurring. And so another way to do it is simply add these with the addition rule, and then you found out the probability of you win one game. What's the probability of winning? Why would you add those two? Because wouldn't you win one game and lose one game automatically mean your brother doing the opposite? Oh, but this goes to the order of it. So this is like, good question right there. Catherine, I think, asked it, or Mary asked it. Thank you, Mary, for asking a question. This is the first game. This is the second game. This is the first. This is the second. So this actually goes into play with the order of the games that occurred, because there's two ways that one game could be won by me. I could win the first game, or I could win the second game. Does that make sense when I say that? I could win the first game, or if I win one game, I could win the first game, or I can win the second game. Don't worry, Ariel, you got this. You got this. You can bring some confidence. Be like, okay, let me, like, I got my notes. I'm reviewing. I'm scaring so many people. No. My intent is not to scare people. If you say or right here, I could either win the first game or I could win the second game. Yeah. And so you can't win only the first game and also win only the second game. I could win the first game or I could win the second game, making them disjoint things right here. So we could add to those probabilities right here. Good probability question right there. You got this. You got this. I think Charlie asked a question about the ANOVA. We're going to do a good 10-minute thing right here. We're going to go a little bit older. I'm going to take a break before the class, but let's do a 320 thing. 201 hangout. We'll do another 201 after this. 320 thing for asking a question. Let's do a 320. Okay. So you're actually going to see some regression right here. So hangout 201. We're going to do a little bit of regression. Put those 201 questions in the chat. We're going to see some regression right here done at a little different of a level. So pretty cool stuff. So let's go look at another regression right here, 320, talking about some sums of squares and the naive model and how we calculate certain things. Let's check it out. So if you're in 201, you know about regression. Let's use our classic height and weight. Just a very simple model to make. If you understand simpler models, you can use that knowledge on more complex models. So whenever we make a model, we want to visualize that model, and we want to ask ourselves what? QQ straight enough, no outliers. What? There's some outliers. There's a not straight enough relationship. These both variables are quantitative. QQ straight enough, no outliers. What? What are the conditions? What's that last condition right here? QQ straight enough, no outliers. What's that last condition? 201, you should know it. QQ, and this goes to 320 also. We're just doing some regression. QQ, straight enough. 100 points in the chat. No outliers. What's that last condition? Last condition would be plot does not, Kaylee got right there, plot does not thicken. Same thing for 320. Now that means the predictive power of the model should be what throughout the model? The predictive power of the model should be what? If you think about the predictive power of the model, we're talking about how it goes around the line, the points around the line. The predictive power of the model, if we have a line, should remain relatively what? The predictive power of the model should remain relatively what? It should remain relatively this. Hence, plot does not thicken. It should remain relatively the what? Evenish, about the same, evenish. So we actually, people often tell me, like, how do we know we fail these conditions? These are p-values. And we covered this a little bit in class today. All of these p-values are what right here? They're statistically significant, which in this test, so 320, you need to know this. Hopefully Charlie or 320 is watching right here. How many of these tests do we fail? We're testing to see if there's a linear relationship. We're testing to see if there's equal spread, like plot thickening. And we're testing to see if the residuals follow a normal pattern. And with low p-values, this is not 201, so don't worry. It's 320. With all these low p-values, we have evidence of a problem here. We fail the linearity test. We fail the for the variable, the x variable, and the overall model. And we fail the equal spread, so there is a problem with plot thickening here to some degree. And we fail the normality of the residuals, which is seen over here on the QQ normality plot, also known as a normal quantile plot, which we have seen in 201 also. It doesn't follow this red line well enough. So what are we trying to do with our regression model? This might be interesting to a lot of 201 to be like, well, what were we trying to do? What we're trying to do is we're creating our first model here. And our first model would actually be, let's add this right here. If you're here for 320, please tell me what this model is called. This model right here is called the what model? Oh, I got to do H equals. This model is called the what model 320. This model that I'm drawing out right here for you right now is called the what model. This model, which is the flat line right here, is called the no knowledge model, and it's called the what model. So this model right here, which is where we calculate it, exactly, all tests fail, but sample size is great. So we would continue to look at the plots. Charlie, great answers right there. Charlie, 100 points. This model that's the no knowledge model, which is the starting point, is the naive model. And this is where we actually calculate the sums of the squared error. So what you would actually calculate from this is you would actually calculate a what from the naive model. Why does it keep defaulting to that? You would actually calculate a what from the naive model. You would actually calculate something's what from the naive model. What is this called right here? 201 should know this. So you're actually calculating something's miss from the naive model, which is its what's from the naive model. So you're actually calculating its what from the naive model. And the naive model is the mean of y bar. So it's residual. That's just a residual. And then what do we do when we say the sums of the squared error? And what would all the residuals add up to? Like if we just added all the residuals right here, if we added the positive and negative residuals, hence why we start squaring them and getting a sums of squared error, what would the residuals add up to if we just did a sum of residuals? If we just summed up all the residuals instead of squaring them, then what would the residuals add up to if we didn't square them? They'd add up to 0 because the line goes through the middle of the data. It's the mean of the data, so it's like a balancing act. But we square them so they're all positive, and then we sum up the squares of the residuals so we can get a sum of squared residuals, sum of squared error. Residuals are error. And Kayla and everyone, great job. This is the practice we need to know for the exam. So what we're going to do is we're now actually in a regression going to not look at this model. That's the starting off point. We're actually going to look at our model. Our model right here is going to be in blue. And that's our model. So then the question becomes, does our model do a better model than the naive model? Just look at that visually. Does our model do a better job than the naive model? Does it look like right now like our model goes through the data better than, and we got some outlier. That's a really big outlier right there. That one actually does worse. If you look at the squared error on this, from the naive model, that's the squared error. And then from the actual model, from our model, the squared error is this. Ooh, so that's got a bigger sums of squared error on that one. But even with that big one right there that's worse, our model does a better job. And so, Charlie, big question here. The goal of our model is to do what to this error calculated from the original data? The goal of our model is to do what to the original error from the naive model? The goal of our model, so there's an R word you should remember, like, oh, we want to do what to this error? Which we'd love it. We'd absolutely love it if we had, actually, that might have been a good graphic. We'd absolutely love it if we had something like this right here. If we had this, this would be amazing, because here's the naive model, which is the mean of y, and then this would be the original error right here. That's the sums of the squared error, should be squares. That's the sums of the squared error from the naive. I wish it was green, because the green is the naive. So this is the sums of the squared from the naive model, and then we're trying to what that error with our model? We're trying to reduce it. Hey, Trevor, good to see you here. We're trying to reduce it. And since we've reduced all the error right here from the naive, so the sums of squared error of the naive minus the sums of the squared error from our model. So how much does our model have an error right now? Tell me the error of my model. And this is going to be really cool right here. Tell me the error of my model right here. How much error does my model have right now? Just tell me a mathematical number for the amount of error in my model. Awesome. Great job, people helping out right there. Does NP solve for success? The amount of expected successes, amount of expected failures. Great job right there. How much error does my model have? My model's the black line right there. How much error does my model have? My model has 0 error. My model has 0 error. So you see right here, this would be 0. What does this equation solve for right now? Solve what this equation solves for. Like, just solve mathematically, even though there's not numbers for those. What does that solve? What does that solve out to? What does that solve out to? My model has no error. My model, which is this line, has no error. Every point is perfectly on it. My model has no error. The error from my model is 0. So I have sums of squared error naive over sums of squared error naive. Mathematically, this will solve out to what? This is the same thing as this. So it's sums of squared error naive over sums of squared error naive. Mathematically, the number that's going to solve for is what? Mathematically, the number it will solve for is what? So what is the mathematic answer to this? So it's this over this. You could literally think of it as like x over x. Because it's just sums of squared error naive solves to 1. What did you just solve for? You solved for the percent of variation in y explained by your model. You just solved for what quantity here, mathematically speaking, because you're looking at how much of the variation in the data is explained by your model. You just solved for what, 201? You just solved for the percent of that's r squared. Because you're looking at how much our model reduces the variation that is inherent in the y variable. Like, our model explains this amount of the variation. You just solve for r squared. That is the mathematical calculations of r squared, is the reduction of the sums of squared error, because we have variation in the y, and how much of that variation is explained by our model right here. To view this visually and to calculate these numbers, we'd actually going to give us the calculations on what is the remainder. So the residual is how much we have not explained. The x is how much we have explained. So what we would do right here is we'd get a total amount of variation, which is the naive. So we could just call this the naive, which is the starting point of variation. And then which one of these is the good number? Which one of these is the good number? Like the number we like, which is our reduction. Which one of these sounds good? Might be easier to say which one sounds bad. So which one of these would be the reduction in the sums of squared error? Which one of these tells us how much the sums of squared error has been reduced by? Because I see residuals, and residuals is how much we miss by. That's unexplained variation. Residuals is the unexplained, and then weight is what we have explained. So if we go right here, and this is the reduction, which is how much we have explained, we go to reduction. So that's how much we've reduced it by. And then if we take the reduction, which is how much we've been able to explain over the naive, that's the r squared right there. And check it out. Look at the output. That value right here, make it appear back on the screen, is that value right there. You thought it was a trick question? No. I try not to be as many trick questions as possible, but the reduction in the sums of squared error is accounted for by the x variable. So the x variable accounts for this much sums of squared error. This is what we haven't accounted for. The total amount of variation would be what the naive has. So this is the reduction right here. Like when we look at our model, reduces the sums of squared error by this amount. So if you had a perfect model, here I can show you a perfect model, you would see that there'd be nothing left over in the residuals. If we just make a perfect model right here where we have m save into lm y tilde x, and if we do a visualization, this is just 1 to 10 explained by 1 to 10. There's your perfect model behind me. So now if you look at the ANOVA table, you will see that there's what for the residuals. It's getting mad saying it's a perfect fit. So now the residuals have 0 variation in them, so there's nothing left unexplained, which means the r squared for this, since there's nothing left unexplained, very clearly type 1 number in the chat, hint, hint. The r squared for this, since there's nothing unexplained right here, will very clearly be what? Since there's nothing left, the model explains everything. It explains 82.5% of the variation. There's no unexplained variation. The r squared very clearly here is going to be 1. So the r squared is going to be 1 because there's no unexplained variation. Our model, there was 82.5. Usually you don't calculate it from that. You would sum these to get the total. And you could also get the total. If you were to go back to here, I need to go way back. You can fit the naive model. When did I fit my model? You can fit the naive model by putting a 1 right here. And then, can we do an ANOVA with this? Yeah, and so here's the original sums of squares, which if you look at the naive, there's the naive. It's doing a little decimal place different. But this is a no x model, which is the mean of y. So this is the mean of the y variable right here because there's no x's in the model. So this is the calculation of the naive model. Charlie, does that help out right here? And Kayla, what do you think, Kayla? Kayla, if you're taking, like you said, taking 320, like if this is all making sense, you're going to hear this again. But these topics connect to 201. They all connect. We talk about statistical significance. We talk about all that good stuff right here. But yes, we'll try to do like one more question right here. We got, we might end because we got, what is it? 145 or 150? I think it's 150, right? Or 250 your time. I'm in Texas. Thank you to everyone who's asking all these questions. This is a pretty good review of these topics right here. A little quick. I think I should know my schedule by now. I've got like like 40, 50 semesters in my head of different schedules. 250, you bet. Last questions. What is your favorite class to teach? And I love all my classes differently. Like, it's like children. It literally is like that. Partial F, we can do a partial F real quickly right here. But my favorite class to teach would probably be 207. Just because, and they took out the lab. I just have to do lab during class. 207 is a class I designed myself, and we got to bring Nerf blasters to campus. We got to do a soda taste test. COVID times, hope we still do that. But I'd bring soda to class, and we'd literally watch YouTube videos and take data on drinking soda with like, we'd be like, okay, let's make a cherry Coke, like a cherry lime Coke. And then people would be making their drinks and just watching YouTube videos. So I missed like doing experiments. We'd do a catapult experiment. My dad would come to class and we do a catapult experiment. So I just like doing experiments. I like collecting data, and that class was more freeform, and I like that. I like the open-endedness. Yeah, I know. I like just doing experiments. Like, hey, let's come to class. Let's drink soda and do this right here. We should have done a coffee taste test thing. Maybe we could do that. Not everyone drinks coffee though. Not everyone drinks soda. So one semester I brought like soda, and everyone's like, I don't drink soda. I'm like, no one drinks soda. It was all right. But 207. A lot of fun. I love 201. All my classes are my favorite for different reasons, but I just like the free form because I would just write random assignments, which some students didn't like. One semester I got destroyed on my 207 reviews. I learned some from that, but some students were very critical. So it was a fun class to grow as an educator too. But one semester they really didn't like me. I mean, not that they hated me, but yeah, anyways. Okay. Let's talk about that partial F test here. We'll put a break in the video. It's just that I made the class pretty tough. Because I can design it. So what's the point of a partial F test? A partial F test is going to allow us to compare what models to what models. So Charlie, whenever go look, it's not that I've ever looked at Rate My Professor. If you go look at my bad reviews, it's from that class. Well, thank you so much, Tara. I appreciate that. I appreciate it. I appreciate it so much. I know I say this a lot, but I really care about my students. I want people to be successful. One of the hardest things is like treating everyone equally. doing everything right here. I want everyone to be treated fairly and equally. That's my biggest goal. It's tough. It's tough. It's tough. Simple versus complex. That's the partial correct right there. Thank you, Kayla. Oh yeah, I try. You gotta show, not tell, right? Gotta show it. So I try to show it with all my actions. If you go all the way from the naive to the full model, what are you actually running right here, Charlie? You are correct. What are you actually running if you go all the way from the full model to the naive, which is the starting off point, which is the mean of y right here, and you go all the way to your big model up here? If you go all the way up, you've actually just run a what? If you go all the way from the naive, you've actually just run a what? Which is what we were just doing a second ago. If you go back to what we were doing a moment ago, we were running this when we were running in ANOVA. We don't have anything in this model, but we can put some more stuff in. Let's just go crazy. If we go right here and we run this ANOVA, then this right here is called a what? This is an f-test. So the full f-test, like just an f-test, the f-test is going to compare your model to the naive. And so we're looking here at what is the leftover variation right here, and then what is it being accounted for by these variables. And does it make sense that height, the majority of the variation in height is actually being accounted for by what in this model? Just take a look. Take a moment, look at the data right here. The majority, we'll go for like 3-4 more minutes because we're going to start class here soon. The majority of the variation in height is being accounted for by what in this model, which you can actually see the statistical significance of it. The majority of the variation in height is being accounted for by what? With everything in the model here, the majority of the variation in height is being accounted for by what? And just go with what your brain tells you. Gender. The majority of the variation in height, that's a lot of sums of squares right there. The reduction in sums of squares, like the ability to explain height, is largely attributed to gender. Weight is doing some explaining. How much people want to weigh is doing some explaining. And there are other variables like how much you play video games. Just interesting that some of these variables come back statistically significant, which means they bring with them new information not accounted for by the other variables in the model in a multiple regression. So this model has a ton of variables. So if we go and do a f-test, we're going all the way from the naive model, which is the starting out point with no variables in it. This has 0 x's when we do right here, where this has all the x's. So that's an f-test. But what is a partial f-test? A partial f-test means we do what? A partial f-test means we're going to start with what already in the model. So think about this. Just look at my scale right here where we talk about the amount of x's in the model. So a partial f-test means we start with what? A partial f-test, so an f-test goes from the naive to your full model. Like you would say, let's compare our model to the naive. So the f-test compares your model to the naive to see the sums of squares reduction from the naive. But a partial f-test, Kayla just rock star, you got it right there. Partial f-test is going to start with some x's in the model, but not all. Well, technically, so good technical thing right here, it could. In this example, you are correct visually the way I drew it right here. It is not going to all of them, but it could. The big thing is you don't usually start here at the naive. That's kind of the big point, is you're not comparing the naive. You're comparing a water model to I'll say it, because we don't have much time. You're comparing a smaller model to a bigger model. Does that make sense right here? You're comparing a model with like 3 variables in it to a model with 6 variables. And you're asking, is there a reduction in the sums of squared error going from the 3 to the 6 variable model? So to do this right here, we need to create a smaller model, oftentimes called a simple model, where we might have something like height being explained by GPA and weight. So why is this going to be called right here a simple model? Comparing it to this complex model, why am I calling it a simple model? And you'll see here in a moment as I do the following. Why is this called a simple model? Why am I going to call this a simple model? Don't make typos. Why am I going to call it a simple model? So it should be clear now why it's called a simple model. The reason it's called a simple model, and so yes, it has 2, and comparing it to the complex, the simple model will have what? Comparing it to the complex, the simple model will have what? So a simple model has less x's. A complex model has more. So it's kind of a comparison thing. Like you're going to compare the 2 models. And then the way this works is we use the same ANOVA where we got the f-test. So this is a full f-test, just known as an f-test. It's just called an f-test. If you just want to call it full f-test or f-test, that's fine. If you say the f-test, we assume you're doing that. But now we add in the simple to the complex, and it's going to do a partial f. So the partial f is going to, instead of using the naive starting point, so the starting point right here on this one is the naive, which has no x's. This uses the simple starting point. So the simple starting point is going to ask us, was there a reduction in the sums of squared error going from the simple model to the complex? And the answer is most definitely yes. The 2 right here stands for the difference in 2 coefficients added to the model. If you look at the output, it looks a lot like our 201 output, but there are more x's in the model right here. And so we see that there is a significant reduction in the sums of squared error going from the 2-variable model to the 4-variable model. Exactly. And so great answers right there. Is this making more sense? The partial f compares a larger model to a smaller model, and then we can ask, is there a significant reduction in the sums of squared error going from the simpler model to the complex model? The complex model has in it with it 4x variables right there, versus the simple model has in it 2x variables. You can see some of the differences between these models, where the r squared for the complex is about 64. Pff, look at that. The r squared for the simple is about 36. The r squared alone would kind of indicate some statistical significance in the difference between the models. But the p-value right here on the partial f is the big one that says, yes, going from the simple to the complex, there's a significant reduction. So it is, since there is a significant, we would want to keep the variables in. We wouldn't drop them. That is exactly right. Charlie, great answers right there. Sorry. Start class teaching in 12 minutes. I'm going to send out the announcements right here. But since we see a significant reduction in the sums of squared error going to the 4-variable model, we would not remove the 2 variables. So I would say, yes, the inclusion of the 2 variables is statistically significant. They bring with them new information that reduces the sums of squared error in a significant way. And the variables themselves, everything but GPA. GPA was not significant in either model, which means it does not bring with it new information. So what you could look at, last but not least, is you could look at removing GPA. And so we could look at the removal of GPA by asking, well, let's put in the, gotta finish up, Ryan. Gotta finish up, man. The p-value on this, on the partial f now, is actually going to be 0.344. And wait, did I lose my mind? Oh, I didn't do GPA. I wanted a difference between the models to be GPA. No, I was looking at models that differ in desired weight. Desired weight is statistically significant. So I need desired weight in the simple model instead of that right there. I think that's got it. There it is, 0.344, which is the p-value for the complex model. So the p-value right here, since there's just one variable being removed, is the p-value for the variable itself. Are we going to have to use R today? You'll have to know how to read R output, know how to read R output, ask those questions, email those questions. I'm going to do some tool 1 here in 10 minutes. So we're going to head off. Puppet Shark, is it time? Yeah. It is time. Email me those questions. I'll be answering questions right after class. I will see everybody soon. Email those questions. Good luck, everybody. 201-320. Let me know if you have questions. Answering them after class.